Today's goal of this lecture is today I will see some example of complete metric space. In previous video I have seen what is the complete metric space and some few example of complete metric space and one use of complete metric space which is actually named as Banach fixed point theory. This is I had seen in my previous video. Today's goal of this lecture, today I will see some example of complete metric space in DP metric space which is known as LP space. Also today I will see some example of complete metric space in submetric space. Okay, this type of example actually very important for higher study. So actually this concept very important for higher study. So please take some time out and try to learn the topic from this video and make points and make notes and save this video with you and keep watching it every small interval. Okay, then you will understand it in better way. At first I will see for each p greater than equal to 1 Rndp is a complete metric space. For this, just recall what is the complete metric space. Complete means every Cauchy sequence is convergent here. Consider XDP a metric space. Then the metric space XD is complete if for every sequence xk belongs to the metric space X such that limit Lm goes to infinity, distance between xm and xl equal to 0. That means the sequence is Cauchy sequence, and if the metric space is complete, then every Cauchy sequence is convergent. That means this is the Cauchy sequence. That means there exists x in the metric space X such that limit k goes to infinity d of xk comma x equal to 0. Now let's see our original goal of this lecture. For each p greater than equal to 1 Rndp is complete metric space where Rd is complete metric space where d equal to usual metric space. With this metric space, real number is complete metric space, we all of us know. Now I will see Rn with respect to the dp metric, means here dp defined as summation I equal to 1 to n absolute value of ai minus bi to the power p to the power 1 over p. dp is defined such type. We have to prove Rn with respect to this dp is a complete metric space. For this, let xk be any Cauchy sequence. And here xk means in Rn x1 equal to x1 1, x2 1 up to xn 1 so on. X superset 2 equal to x2 1, x2 2, sorry here 2, x1 2, x2 2 up to xn2 so on. Similarly, xn equal to xn1 xn2 xnn so on. Okay, and I will create this type of sequence, and I will say this type of sequence means here x1n n equal to 1 to infinity, here x2n n equal to 1 to infinity, and here xnn n equal to 1 to infinity. I will prove this is Cauchy sequence. Then in our next goal, I will say this converges to x1, this converges to x2, and this converges to xn, where x equal to this x1 comma x2 up to xn so on. And our given sequence xk, we have to show this xk converges to this x. Okay, and we have to show this x belongs to the LP metric space. This is our goal of this proof. Actually, we have to prove this part. At first, construct one sequence which look like such type, and we have to create such type of sequence x1n, x2n, xnn, such type of sequence. And actually xk, which is the Cauchy sequence in LP, xk converges to this x, where x equal to x1, x2, xn so on, and we have to show this x belongs to LP. Then our proof would be done. I hope my all viewers have understood this. Now let's see the proof clearly. That means since I have considered xk be a Cauchy sequence, then limit Lm goes to infinity dp xl comma xm equal to 0. Since I have considered xk is a Cauchy sequence, and we aim to show there exists a vector x in Rn such that limit k goes to 0 dp xk comma x equal to 0. This is our proof, and this vector x would be such type. For this, we claim that for each I equal to 1 to n, the component x of the sequence xik be a Cauchy sequence. For each I equal to 1 to n, xil minus xim less than equal to x1l minus x1m plus x2l minus x2m plus x3l minus x3m up to xnl minus xnm. Actually, we can write this is less than equal to summation I equal to 1 to n absolute value of xil minus xim to the power p to the power 1 over p. And this is actually less than equal to, this means dp xl xm, sorry, here l, here m, xl xm, and as lm tends to infinity, since I have considered xik be a Cauchy sequence, that means this part goes to 0 as lm tends to infinity. That means this part goes to 0, and since this part goes to 0, therefore this part actually goes to 0. That means each component of the sequence xik, each component of the sequence is a Cauchy sequence. Have you understood our claim? Our claim for each I equal to 1 to n, where I equal to 1 to n, each component is a Cauchy sequence. And since R with respect to D is a complete metric space, therefore each component converges to a vector x belongs to Rn, where x equal to x1, x2, so on. I have told at first our goal, we have to show each component converges to x1, x2, xn, and this is each component converges because we all of us know R with respect to usual metric space always be convergent. That means our given sequence xk actually converges to this vector. Our goal has proved. Now we have to show this vector x actually belongs to the LP. Limit k goes to infinity, dp xk x means limit k goes to infinity, summation I equal to 1 to k, absolute value of xik minus xi to the power p to the power 1 over p, and we can write this as summation I equal to 1 to k, limit k goes to infinity, xik minus xi to the power p whole to the power 1 over p. And since R is complete metric space, therefore each component, this part actually goes to 0. So obviously whole part goes to, this summation goes to 0. Therefore our given Cauchy sequence xk, this is converges to this x belongs to Rn, where x equal to the vector x1, x2, xn. Okay? Well, I hope my all viewers have understood clearly why Rn in dp metric space is a complete metric space. Our next example, next I will see set of all continuous function which is defined on the closed interval AB. I will see in this interval, if we consider D1 metric space, which is denoted as maximum of t belongs to closed AB, absolute value of xt minus yt dt, in this metric space, this space x comma d1 is complete metric space. But if we consider d2 metric space, which is actually integration a to b, absolute value of xt minus yt dt, this is not a complete metric space. Why not? This is very interesting. Here the space is similar, but I have defined to different metric and xd1 is complete. Okay, but xd2 is not complete. Okay, at first consider CAB in the metric space D1 is complete. For this, consider XM be a Cauchy sequence in CAB. Then, given epsilon greater than 0, there exists a capital natural number n such that for all mn greater than equal to capital N, distance between xm and xn, which is equal to actually maximum t belongs to closed AB, absolute value of xmt minus xnt less than epsilon, and this is true for all m and n greater than equal to n naught. As xmt minus xnt less than equal to maximum t belongs to AB, absolute value of xmt minus xnt, therefore that imply, since this is less than epsilon, then that imply absolute value of xmt minus xnt less than epsilon, and obviously this is true for all mn greater than equal to n naught, and since this is true for all t, so if we fix one t naught, then that imply absolute value of xmt naught minus xnt naught less than epsilon. Okay, and this is true for all mn greater than equal to n naught. I hope my all viewers have understood this, and that imply x1 t naught x2 t naught is a sequence in the real line. So actually xm t naught is a Cauchy sequence in the real line, means R is a complete metric space. So that means obviously this sequence xm t naught would be converges, and this converges to, consider this converges to x t naught, which is actually belongs to R. Now define one x which is defined from closed interval AB to R such that xt equal to limit m goes to infinity xm to t. Now we have to show xm converges to x, and this x actually belongs to CAB. Okay, since maximum t belongs to AB, absolute value of xmt minus xnt less than epsilon, and this is true for all mn greater than n. Since this is true for all t, if we take as n tends to infinity, then I will get maximum t belongs to closed AB, absolute value of xmt minus xt less than epsilon. This is true for all mn greater than equal to capital N, and this is true for all t also. That imply, from this expression we can tell, since maximum of xmt minus xt less than epsilon, that means obviously absolute value of xmt minus xt also less than epsilon, or for all m greater than equal to n. This is true, xm converges to x, and this is true for all t. That means this convergence is actually uniform convergence. So since xmt converges uniformly xt, that means obviously this xt always continuous function. So since xmt converges to xt uniformly, that means obviously this x belongs to CAB. Okay, now I will say same space but not complete in D2 metric space, where D2 equal to integration a to b absolute value of xt minus yt dt. I will see in this metric space the space is not complete. For this, consider x be the set of all continuous function. For short calculation, here I will consider a be equal to 0 to 1. I will see the metric space which is denoted as integration 0 to 1 absolute value of xt minus yt dt. I will see the metric space xd is not complete when I will define this type of metric. Why not? Let's see. For this, consider xm be a Cauchy sequence, and for every epsilon greater than 0, distance between xm and xn less than epsilon, and this is true for all m and n greater than equal to capital N. And defined one new function such type xmt equal to 0 when t belongs to closed 0 open closed half, xmt equal to 1 when t belongs to am to 1, and here am means such type half to 1 half plus 1 over m. That means the picture would be such type, here 0 and here 1. When 0 to half, then the value is 0. When am to 1, then the value would be such type 1. Consider this is the half and this is am. Am to 1, the value is 1. In between the point half to am, the graph would be such type, and am to 1, this value is 1. I hope my all viewers have understood this graph easily. Okay? Oh well. Now, since the function is defined as integration 0 to 1 absolute value of xt minus yt dt, here for different value of m, here the graph would be different. Now, consider the distance between xm and x, which is equal to integration 0 to 1 xmt minus xt dx, and this is equal to 0 to half. We can break this as 0 to half xmt minus xt dx plus half to am xmt minus xt dx plus am to 1 xmt minus xt dx. Okay, and here xmt minus xt dx on the interval 0 to half, the value is 0, therefore this integration value would be 0. And when half to am, here when m tends to infinity, then this value also would be half. Therefore, half to half, that means since both integrals same, so this value also tends to 0. And here am to 1, that means half plus 1 over m to 1, and here the value of xmt would be such type am to 1, value of xmt is 1 minus xt dx, and here am means half plus 1 over m to 1. Therefore, as m tends to infinity, am tends to half. Therefore, here the value of integration is half to 1 when m tends to infinity. And in this interval, the value of xt also would be 1. So, 1 minus 1, that means this is also tends to 0. That means d of xm comma x tends to 0. Okay? But value of xt is 0 when t belongs to 0 to half and xt is 1 when t belongs to m to 1. Therefore, from this expression we can tell xt does not continuous function. Therefore, xm does not converges to continuous function x. So, this matrix in this matrix space C01, here I have considered AB as a 01, not be complete. I hope my all viewers have understood this concept easily. Okay? Oh well. That means the same space may be complete one matrix space. But if we change the matrix space, then this space cannot be complete. I hope my all viewers have understood. This concept is very important concept. Today I will stop here. In my next video I will discuss this topic again. Because this topic is very important for higher study. See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.